Yeah, thank you. Yeah, thank you for the nice introduction. Hi, everyone. So today I'm going to talk about one of our recent work. Our recent work on non-convex optimization and a new concept of quantum tunneling walks. And this is a joint work with Yizhi Liu, who is currently a PhD student at MIT, and also Professor Weijie Su at UPenn. So the topic of this talk is going to be about optimization. So optimization is probably one of the most important problems, I guess, in applied math. So it's basically a very fundamental problem that in general we want to talk about. Okay, so we have an input, so we have a function f and basically an input that is in r-dimensional space and it's mapped in R. And basically our goal is to minimize this kind of function fx. Okay, so I guess in general for optimization, you can also talk about maximization problem, but here I guess it's just like an inverse problem. You just like take a minus sign, it becomes a minimization problem. So in general, let's for the talk today talk about minimization. So such problem is actually widely applied in applied math, computer science, physics, etc. And basically, I think for the topic today, I guess in general, this is like a theory work, and we want to understand what is like a provable guarantee for solving such kind of optimization problem. So in particular, can we prove that, for instance, for like there's like a convergence guarantee. And in general, for instance, like in convex optimization, this actually has been widely studied that actually, convex optimization can be solved in polynomial time if you can query the function f here. So by query here, after all, you need to have a way to understand what this function f is. So basically, such kind of query is basically say, okay, so for instance, you are interested in a certain point x, and I tell you the corresponding function value fx. So basically, using this kind of query box, you can use like ellipsoid method, like interior point method, etc., to solve the convex optimization problem in polynomial time. So the main topic today is basically non-convex optimization. So basically, this is the case that the corresponding function is non-convex. So why are we actually interested in non-convex optimization? Is that basically, for instance, like in the computer science domain, like training a machine learning model is basically equivalent to optimizing a certain loss function. But it's just like in general, for instance, like especially for instance, like in training neural networks, the corresponding loss function is very non-convex in general. For instance, when we talk about a convex function, its corresponding landscape is basically going to be looking like this, where actually we have a unique local minimum, which is the global one. But for instance, if you draw a landscape of a neural network, a corresponding loss function of a neural network is probably going to be much more complicated. It's probably going to be looking like this, and it just has so many local minima. And I guess in general, speaking of this, we probably need like a more general strategy that hopefully, is in general, it is known that non-convex optimization cannot be, it's probably NP hard in general, and we shouldn't aim at like polynomial time algorithm. But hopefully we can still get some guarantee, under some circumstances, or maybe hopefully some algorithm are still good that in general can be finding a good local minimum or maybe even global minimum. So like a general strategy that people use is the stochastic gradient descent. So stochastic gradient descent is something natural, right? So you are currently at a point, say at a point xk. So it's basically a iterative algorithm that for the next step, it is basically for the current step, you're calling the gradient. So you're calling the gradient at this point. And also for many problems, there are like a stochasticity here. So basically, I take the gradient and also take the stochasticity, and there's a specific learning rate like an S here. Then basically you move your point, current point from xk to the next point xk plus 1 according to this kind of iterative formula here. So basically the stochastic gradient descent, this is like a simple algorithm, and basically this is like the working horse in a lot of like a practical algorithm that people use. For instance, like Adam, like Anagrad is basically like improved version of the stochastic gradient descent. However, the stochastic gradient descent in general has some kind of issue. So in particular, it is a little bit difficult to make exploration in the optimization landscape. So for instance, assume that you have like such kind of function, and basically the global minimum of this this function is basically in the very right hand side of, and this is basically like a one-dimensional function. And let's say that global minimum is in the very right hand side of this kind of landscape. But assume that if for instance you begin from the left hand side, so basically you do stochastic gradient descent. So basically, you are around this point. Maybe due to stochasticity, you can like go through this and this. But unfortunately, this is really high for like stochastic gradient descent, right? It's in general very difficult that you can actually jump through that and then jump through that. Basically, this kind of things. So, in general, this is really difficult. And in general, exploration in the optimization landscape is the most, one of the most, outstanding issue that basically such kind of optimization problem should address. And basically, I mean, the idea that we are going to think about this, okay, so we think about, okay, so I mean, applying this kind of stochastic gradient descent method, we need to, okay, so jump through this kind of high landscapes. So in terms of quantum mechanics, I guess in general, I mean, there is a concept called quantum tunneling that actually such kind of non-convex landscapes commonly appear. So the observation is that, okay, so for instance, I mean, here is basically we have like a potential here that we need to jump through here. And basically imagine that you have like a classical dynamics or basically classical mechanical waves that is evolving on the left-hand side. So basically for a classical mechanical wave, you really need to, okay, so if you jump through that, you really need to evolve, I mean, jump through that and going to the right-hand side. But on the other hand, if you have like a quantum wave function that evolve like a Schrodinger's equation, so basically the probability of getting from the left-hand side to the right-hand side can be more non-trivial. So basically, this is the observation that in general for the talk today, I'm going to talk about, okay, so if you have like a Schrodinger's equation, if we evolve the corresponding dynamics, how can this be helpful for optimization? Or maybe in the future can also be applied to machine learning problems. So here, I mean, basically we are talking about such kind of Schrodinger's equation that in general, okay, so this function f is basically the function that we are going to optimize. And basically we treat the function we are going to optimize here as the potential function of the Schrodinger's equation. And here, basically we can also, I mean, you can regard this h as basically like a quantum learning rate. So in the standard Schrodinger's equation, this is like the Planck constant. But here, I mean, in terms of the dynamics here, I mean, we treat this h, I mean, the quantum learning rate as a relatively small value that can also be tuned throughout the optimization algorithm. So basically, for this kind of problem, that basically if you have a Schrodinger's equation, that you can evolve this. So basically, so basically, when the case where h is small, then basically, I mean, such kind of solving such kind of Schrodinger's equation, I mean, this is relatively well studied in mathematical physics, and there is like semi-classical analysis, such as the WKB approximation, that basically, for instance, you have like a one-dimensional problem where this potential function v is one-dimensional, and you consider this corresponding eigenfunction, then this has like a closed solution is basically looking like this. So in particular, the quantum wave function is basically, I mean, the eigenfunction is basically going to have the behavior that the main part that basically you can see is basically this part that are actually going to depend on the integral here. So it's basically going to depend on the integral of the difference between the potential function v and also the corresponding eigenvalue e here. So this is like an eigensolution of the WKB approximation. And in terms of the dynamics, I guess this is going to be giving you like a significantly different behavior compared to the classical counterpart. So in particular about like the classical dynamics, and if you can see, I mean, here because I mean for the evolution of the Schrodinger's equation is like a continuous time dynamics. So basically for like making like a kind of like apple to apple comparison. So I'm also talking about like classical dynamics. So basically if you consider like a continuous time limit of the of the stochastic gradient descent. So that is basically okay. So you have like a classical consider like a classical stochastic differential equation. Basically, I mean, also you have hopefully, I mean, you are following this kind of gradient flow. Then basically, it is like this kind of Langevin equation that the time dependence term is basically like a minus of the corresponding gradient, and also because of the stochasticity, is basically like this kind of Brownian motion term. So basically, this kind of equation, also known as the Langevin equation, can characterize the classical stochastic gradient descent. And also on the other hand, quantumly, we consider such kind of Schrodinger's equation. So basically, these are like the two dynamics that we are making the comparison with. And basically talking about the convergence rate. So classically, so if you want to analyze, okay, so we have this kind of Langevin equation, and what is like the convergence rate that for this case, I mean, for this case, you move from the left-hand side to the right-hand side. So basically the cost is like exponential in terms of the HF. The HF is the absolute height of the corresponding potential here. So basically, I mean, there's like the highest point to like this point compared to the value of the well here. So this is like the absolute difference of the corresponding function value. So basically, this is the HF divided by the S, whereas this S is the learning rate of this kind of Langevin equation. But on the other hand, if you consider like the corresponding quantum dynamics, it is also, I mean, the time that actually you can evolve from the left-hand side to the right-hand side is also like an exponential kind of term. But basically, what is actually in exponential is different. So here, the S0 is basically such kind of integral that basically you integrate the the function value with the square root, this kind of square root of f from this function value to this function value. So basically, I mean, it's more like what is actually, I mean, in this kind of, I mean, in this kind of shadow of this kind of function, instead of only like the absolute height, that is actually going to influence the corresponding convergence rate. So in terms of this, I guess in general, basically, you can see the idea that actually we want to basically simulate this kind of Schrodinger's equation. I mean, as long as we have this kind of potential f and want to simulate this and want to see, okay, so I mean, what is the behavior of solving such kind of optimization problem? So I like the first question that we should probably address is that, okay, so I mean, it's good that you can talk about this kind of quantum dynamics, but can we actually efficiently simulate the Schrodinger's equation? I mean, even in a high-dimensional case where the function f is basically like a high-dimensional potential. So this is the first problem that we should address. And basically, throughout the talk today, I mean, the assumption that we make is that we have like a quantum evaluation oracle in the sense that, okay, so I mean, this is like an oracle that has two registers. So we have a register for the input x, and also we have another a register that can store the function value. So basically, you can use superposition query of this oracle, and basically, if the input is x and z, it returns you the values of x and fx plus z here. So for arbitrary x and z here. So this is like a quantum evaluation oracle that I'm going to use throughout the talk today. And this is just like a standard assumption for quantum algorithm. I mean, this is typically assumed in a lot of quantum algorithm doing continuous optimization that you have this kind of continuous function f here. So in practice, I mean, basically for the talk today, I mean, in general, talking about like universal quantum algorithm here. So I mean, you can imagine that, for instance, I mean, I'm talking about real numbers here. So maybe you can imagine that this probably going to be all these values of x and z can potentially be stored in like floating point numbers or maybe fixed point numbers. But I mean, basically, I mean, we just assume that actually all these values are stored with like a sufficiently high precision that, okay, basically, I mean, in the talk, I'm not going to talk about, okay, what is like the approximation error if we explore everything by basically like floating point numbers, etc. But basically, we assume that we have this kind of real number registers. So basically, I mean, the point of considering such kind of oracle, so assume that basically is basically the point that if the function this function can be computed by a classical circuit, so just like arithmetic operations, such as just like plus, minus, like multiplication, division, etc. Then basically you just do the corresponding things like quantum linear superposition. So basically, if you have like arithmetic circuit to calculate a corresponding function f, you can also assume that basically you have like a corresponding arithmetic circuit in a quantum situation that of roughly speaking the same size, that you can calculate the corresponding function f here. So basically, there is a previous work that actually based on this oracle, based on this kind of quantum evaluation oracle about like the cause of simulating the Schrodinger's equation. So basically, the cause of simulating the Schrodinger's equation is basically like linear dependence in terms of the simulation time, the t here, and also the norm of the function f here. But after that, in general, the other complexities, I mean, the other parts in general, I mean, it's only like a log term, and basically the main cause comes from the simulation time. And after the function is fixed, it's basically about the simulation time here. Okay, so basically, I mean, we have good understanding about like the simulation causes. Basically, I mean, like a linear dependence in terms of simulation time. I guess the main topic today, I mean, basically the main thing that I should explain today is that, okay, so if you evolve like the Schrodinger's equation for solving such kind of high-dimensional optimization problem, what is the behavior? So this is the most important question that we should address. And basically, I think this is our main result. I mean, like an informal result that basically for non-convex functions, I guess in general, I mean, I have to admit that in general, non-convex optimization is super difficult. But basically, we can address the case that if the non-convex function are actually having the case that local minima are actually having a nearly equal value. So I think in general, we can also deal with the case that actually the function value is not exactly the same, but actually near each other. That in general, in the case that actually all the local minima are actually global. In this kind of sense that we observe the phenomenon that actually the evolution of the Schrodinger's equation takes like, okay, so on the one hand, basically, I mean, between like two local minima here, it is actually having the phenomenon of the quantum tunneling, and basically this kind of strength of the quantum tunneling can be described by the one-dimensional WKB approximation. And after that, okay, so this is like pairwise, I mean, pairwise strength between two local minima. We have this kind of quantum tunneling phenomenon. But overall, on the other hand, the overall behavior, okay, so you have a lot of local minima in general, right? So the behavior about like, I mean, in general, the overall dynamics between the local minima actually is having like a behavior of the quantum walk, right? So basically locally a pairwise kind of a pairwise strength between two local minima is basically due to the tunneling and the overall dependence. So if you have like different local minima, you want to understand the overall behavior of the dynamics, that is actually having like a quantum walk kind of behavior, and that is the reason why we coin this term quantum tunneling walk. Okay, so basically, I guess let's make a little bit of further explanation here, and I guess here maybe I think the most, from my perspective, I think the most important point that we still need to make further improvements is probably this part. Okay, so we can currently only deal with the case that the functions here actually having the case that their local minima actually have equal values. So I guess here is probably, a first question that I want to discuss a little bit, that actually, if I want to make, I make a very brief Q&A here. So why do we actually have to make this assumption that actually the local minima here are global here? So otherwise, I guess, there are actually some non-trivial math here. So maybe there can be the situation if you imagine that, okay, so you have such kind of, non-convex function. We are a little bit, in short of math to deal with such kind of optimization. If, for instance, if the ground state, in one of the well is actually an expected state of the other well. So, basically the assumption of having the local minima to be global is that, in this kind of case, we basically study, we consider the substates that is actually spanned by all the local ground states of all the local wells here. So basically, we have like a further analysis along this line. But if it is the case that, for instance, there can be like crosstalk between, like ground states of one of the well, but like excited states on the other wells. There are some non-trivial math here that probably needs future work to further study here. Probably another question. You can understand probably there are technical difficulties here, but for instance, if you want to understand, okay, why this is like a still interesting problem. Basically, if all the local minima are global, and for instance, if you reach one of the local minima, the function values is probably going to be quite same compared to the other local minima. So here, I guess our justification is that, okay, so you want to study non-convex problems. Optimization is definitely very important. It is actually a very important goal, but there are some other important goals. Typically people do want to understand if you have like in general complicated landscape. For instance, simply generalization. So generalization is a particular observation that in general, okay, so maybe some of the local minimum, they probably, if you change like the parameters of the corresponding function, this some of the local minima, maybe it generalizes better that, okay, hopefully this is still like a local minima for a lot of different models. But if for some other local minima, maybe the generalization kind of behavior is probably not as good as others. So this is like actually an important perspective. And basically for the perspective of this work, it's probably more on the generalization side rather than optimization side. And then basically a main problem that we study here is that, okay, so we assume that, okay, we have a function that actually is local minima actually global. And basically we talk about the problem that, okay, we want to study from one of the local minima, and basically we want to find all the other local minima with similar function values. So this is basically like a problem. We start from like a local minima and find the others. We have basically the starting point we know, and actually we know what is actually basically the function values of these local minima or global minima.
We have two
Yes.
questions. Yeah. Okay.
Yes.
Okay, I suppose your quantum dynamics follows the Schrödinger's equation, which is it's a closed system, right?
Yes, right.
So we are not expecting the system will transition to the ground state to focus on your local minimum or global minimum. It's a unitary evolution.
Yes, it is a unitary evolution.
Yes, yeah. So then the tunneling goes one way, and the tunneling goes the other way as well. So as time goes by, are you expecting the wave function will be focusing more and more on the global minimum? I'm a little bit lost here, but it won't. Unless you introduce dissipation. I'm a little bit lost here. That's all. Yeah.
Sorry. Maybe I can make a further explanation here. What is the point of making you getting lost here? Can you maybe summarize that again?
So if your system is open and you introduce a dissipation, and then the whole system will gradually go to lower and lower energy. But if it's a closed system and energy is conserved and the wave function evolves unitarily, and it will just goes back and forth.
Yes.
Yeah.
Yes, it will go back and forth. Yeah, and actually, this is a good point. I think in the later part, I'm going to, going to introduce more about like the concept of quantum walk. And actually, in general, for quantum walk, it is unitary, and I think it is actually a thing that you people need to specify that. Okay, so you have this kind of going back and forth. I mean, basically, I mean, I do want to reach. The other. For instance, you start from this point. I do want to reach the other side. You know, there are like quantum tunneling. I mean, as someone is going to the other side, and it is actually going, but also this can go back and forth in general. So basically, the point is that you need to find a time to make a measurement, and hopefully, okay, so you make a measurement. I mean, it's probably like the unitary kind of dynamics is not that perfect. That okay, you have probability that it can go back, right? But basically, basically in terms of the quantum walk, this is like, I mean, you have this kind of graph structure between the local minima. You do have this kind of mixing properties that in terms of this dynamics, if you, you have like a mechanism to choose the measurement time, you can still have a non-trivial probability to reach the other side. I mean, basically you need to make a measurement. So I guess I will probably make a little bit more explanation.
How do you determine the time? How do you determine the time to collapse the wave function? That's I will explain.
Yeah, I will talk about this.
Okay, thank you.
Okay, so yeah, thanks for the question. I think mainly because basically for the main problem that I'm going to introduce here is that okay, so I'm talking about a problem that we have one of the local minima, and basically I want to find all the other local minima with similar function values. So basically the thing is basically like this. So this is like a main result, and also this main result actually contains like a time here. So basically the thing is like this. So assume that initially you are actually at this kind of local minima here. So basically, to solve this kind of problem, they will find all of the local minima here. So basically, we take this kind of time. So basically, we take this kind of this time tau. We should actually basically a polynomial in terms of n. The n here is the number of global minima. And basically, there is another important parameter here, the delta E, which is the minimum spectral gap of the Hamiltonian. And basically, we can show that actually in terms of this algorithm, basically the minimum spectral gap is actually having this kind of behavior. Where actually it is having like a polynomial term in terms of the age, the quantum learning rate here. And also it is going to be have like exponential term, the exponential of like a minus S0 divided by h. So this S0 is basically like a constant that depends only on the function f here. And this h is basically like the quantum learning rate here. So you see basically this is like probably this e to the minus S0 divided by h is probably the most important, like the crucial and actually the costly term in terms of this kind of quantum tunneling walk. So basically the thing, for further explaining the question is that basically, in terms of the dynamics that we do is that basically we have an upper bound. So we have an upper bound of tau here, which is basically this polynomial of n divided by this delta E here. So we have this upper bound. And basically we sample a uniformly random time from the interval from 0 to tau here. So we have a uniformly random time that is peaked here. So basically the dynamics that, okay, we pick such kind of time uniformly from this interval, and we evolve the corresponding Schrödinger's equation for this time length, and then we do a measurement. So basically the point is that if we do this kind of dynamics, we can have a non-trivial probability. Basically, we can find all the other local minima, basically like this. So I think for the later part of the quantum walk, I'm going to further explain why do we actually consider such kind of dynamics. But maybe here, I think I do want to make like a further comparison to understand what is like the difference between the quantum dynamics and the classical dynamics. So the classical dynamics here is basically the Langevin equation. Basically, as I briefly explained, basically, if you want to consider such kind of landscape, and basically if you move from the left-hand side to the right-hand side, so basically the cos is basically like in the absolute, basically the absolute height, this kind of HF is going to influence this. And this can also be written in this kind of, this kind of form that in general, okay, the time cost is like 1 divided by this delta S, and this lambda S, and this lambda S is basically in this kind of exponential of this kind of 2 times the HF divided by the classical learning rate S. So there is like a classical study about Langevin, the dynamics of the Langevin dynamics and its behavior in terms of solving non-optimization problem in the Shisu and Jordan's work. And basically our work is like, we are actually quite motivated by this work. And I think in some sense, we like quantize their, basically they have analysis for the spectral gap of this kind of, non-convex function. Basically in some sense, we quantize their work, but actually we have a good understanding about the quantum, the behavior of the quantum dynamics here. So basically, as I just mentioned, is basically like the quantum time cost is basically like a polynomial of n, wherein it's the number of local minima divided by the delta E here. And the most like outstanding difference here is that basically, I mean, what is actually happening in the exponential here compared to the classical counterpart, where actually the HF is more on like the in terms of the absolute height here. But our S0 here is basically, I mean, in the quantum dynamics, basically in terms of this kind of, I mean, it's more like an integral kind of behavior instead of only depending on the absolute height.
Can I ask a question?
And basically,
So we've got a
yes, please.
In the classical case, why does no dependence on the number of global optima appear, or is it like agnostic to it or something? Why is there no like n?
Yes. I guess, I mean, yes. Classically, I mean, in terms of finding all the local minima here, it also requires to actually, I mean, find, for instance, I mean, if there are like a local minimum here, there's classically time complex should also have like n time dependence. So here, I mean, I think what is actually in the frame here is in general about like the convergence rate. That, okay, for instance, you reach one of the local minima here. I think classically it is probably only depend on the lambda s here, but quantumly, I guess, in terms of the behavior of the quantum walk, I think it necessarily going to have a polynomial dependence in terms of. But of course, classic, if you want to find all the local minima, it's also going to have an independence. Okay, so basically, I mean, this is like a comparison between the classical and the quantum setting here. And the main message here, okay, so it's basically about like the properties of the landscape. That basically, I mean, about the integral properties, so like the width and sharpness of barriers. So this is like the most significant difference between the classical dynamics and quantum dynamics. But also on the other hand, I mean, in terms of, I mean, the exponential term can also have, I mean, for instance, like the flatness of the minimum period is actually also going to influence what is actually, I mean, the behavior of H and S here. So imagine that in particular, I mean, if for instance at some point, I mean, like for instance, if this potential is really sharp, I mean, it's really sharp. For instance, I mean, this part is very thin here, but it's actually super high. I mean, in general, for this case, it's actually simpler for the quantum case, but it's still going to be difficult for the classical case. That actually the HF corresponding HF is large. And also on the other hand, in terms of the distribution of the well, so that's basically the position of the local minima, they are actually going to be also having like a polynomial coefficient that influence the corresponding dynamics. So in general, I mean, there's like a handle that for different properties of the landscape that actually going to have an exponential influence or the polynomial influence of the corresponding time cost here. So here is basically about like I think I basically finished the first part about like the motivation is basically like a general, I mean, like an informal version of our main result. So I think here, maybe some of the audiences here, I'm not sure if you're totally familiar with the definition of quantum walk. So I guess maybe let me also briefly explain what is like a behavior of a quantum walk. So quantum walk is actually, I mean, in general, we can talk about like quantum walks on like graphs, I mean, like discrete objects. And basically this is like a quantum analog of a classical random walk. But basically the main point is that actually we replace a classical probabilities by amplitudes. Okay, so basically the thing is that, okay, so actually, for instance, if you consider like a classical one-dimensional walk, you just like have an axis. And for instance, I mean, you only walk on integer points that actually you move forward one step with probably a half, and also with probably a half, you walk backward. So basically, you just consider this and you walk for say like 100 steps. So basically, you are going to have like a behavior, like basically like central limit theorem, that you are going to have like a classical probability distribution like this. But on the other hand, if you consider like a quantum walk, basically the thing that you are going to have, for instance, you walk for 100 steps, you are going to have like a dynamics have this kind of behavior. So basically, I mean, if you walk like this, I mean, it's not in general going to converge. So what is actually, I mean, the things behind? The things behind is that basically the quantum walk here is like a unitary dynamics. So in particular, for instance, let's in particular have this kind of graph. I mean, for this graph, you can write down as Laplacian matrix, and Laplacian matrix that basically, I mean, let's for simplicity talk about such kind of like a simple graph. So as long as you have an edge, for instance, have an edge between 1 and 2 here. So basically for the entry in the first column and the second, in the first row and second column here, you're going to have a 1 here. And otherwise, I mean, if there is no edge, you just have like a 0 here. We don't have an edge between 1 and 4 here. And basically also for the diagonal term is going to be the minus of the degree of the corresponding vertices here. So if you have a Laplacian of the graph here, and basically you can consider like a classical random walk, which is basically the classical random walk is actually having like a dynamics like this, where actually, I mean, you start with like a classical, I mean, with like a probability distribution on these vertices here, and you can correspondingly evolve the dynamics where this is like a linear dynamics, and basically the linearity here is actually taken control by the Laplacian L. So the quantum walk that we studied here is that basically, I mean, we for all the vertices here, we have amplitude. We have amplitude here, and basically dynamics is still like a linear dynamics with the most outstanding differentiation to be actually the dynamics is having like an imaginary term. So having an imaginary term, having imaginary I here is actually going to make the significant behavior. I mean, for instance, I have this figure between the significant behavior between one-dimensional walks. So actually having this kind of thing is going to be making a significant thing. It's basically the math is like it's basically like this. So the Laplacian L here is actually a negative semi-definite matrix, and in particular, I mean, it is known that actually 0 is an eigenvalue with a uniform vector being its eigenvector here. So I mean, if you furthermore consider, for instance, I mean, in general here, let's talk about like a connected graph. I mean, we do have like connected graph that in general, okay, so I mean, we have like a general landscape. You can, I mean, like a weighted graph is always connected. And in general, for this kind of, I mean, we have this kind of local minima. You consider corresponding graph here. It's like a connected graph. But for the connected graph, actually, the eigenvalue 0 is actually having a single multiplicity. That is basically to say all the other eigenvalues of this graph has actually eigenvalues strictly smaller than 0. And in particular, if you consider like a random walk on this classical graph, actually, it makes this to the uniform distribution here. So the point is that basically, if you have this kind of, I mean, distribution P of t, actually, I mean, you have like an initial distribution P of 0, and you evolve according to time t here. So basically, if this e to the lt here, you can make an eigen decomposition, and basically, it is going to be looking like this kind of form. So the important observation here is that, okay, so we know that actually the Laplacian L is a negative semi-definite matrix. And basically, I mean, all these parts, I mean, for all the eigenvalues are not equal to 0, it is strictly smaller than 0. And if you, I mean, for this part, I mean, if t goes to infinity, this is actually going to be going to 0 here. And actually, to be more precise here, so as long as you have like a spectral gap, so where delta is like the spectral gap of the graph, that is to say all the other eigenvalues other than eigenvalue 0 is smaller than or equal to minus delta here. So basically, you know that, okay, so evolve for a time like log 1 or epsilon divided by delta. Then basically this e to the lambda t here is already at most epsilon here. You know that basically, I mean, I mean, like the total variation distance between this kind of P of t here compared to the u here is actually already is going to be at most epsilon here. So this is like a convergence rate of the classical random walk. But actually for the quantum walk, the story is totally different. I think as one of the audience just asked, okay, so I mean, in general, okay, the Schrödinger's equation is actually like a unitary dynamics. I mean, in general, it just keeps rotating and does not converge. Right, so you cannot imagine that, okay, similar to the classical analysis, I mean, you have this kind of term that actually going to 0, but if you have like an I here, so if like e to the I lambda t here, it's just like in general keep rotating and does not converge in general, right? So this is a thing that we need to address, and in particular, I mean, people want to talk about, okay, so although like quantum walk is like a unitary dynamics, but still, okay, hopefully we can still have a way to understand this convergence behavior. I mean, like it mixes to a specific like a distribution here. So this is like a common solution that actually when people study the quantum walk, that okay, so although like for like the time, for like you just imagine for a fixed time like the t here, when t goes to infinity, this does not actually have like a limit distribution. But actually we can do the thing like we have like a fixed time, which is like a fixed time capital T here. And basically we take the n time, this t uniformly from this interval from 0 to the capital T here. Actually, it is having a limiting distribution. In general, this is actually going to be very helpful to understand the behavior of the corresponding quantum walk. So why is this the case? So actually, let me do a little bit, I mean, quick analysis here. So basically, I mean, as the thing I'm describing here, so if you take a small t, okay, uniformly from a large interval from 0 to capital T here. So then the probability that actually you reach from A to B then is basically going to be this kind of integral, right? Because actually you are taking like a uniform time t, small t here, taken from this interval 0 to capital T here. You're actually having this kind of interval here, and what actually going to be the probability is going to be this value here. So it turns out that actually, I mean, making some further eigen decomposition, you make some calculations here. So basically, it is actually going to have such kind of form here. And furthermore, for such kind of form here, I mean, if you have the, I mean, here we have having actually a slightly stronger, I mean, assumption for the spectrum of the matrix A here. So basically, we assume that actually we have, I mean, basically this matrix is in general non-degenerate, which means does not have eigenvalues to have the same, actually have for any eigenvalue it does not have multiplicity, and actually we also have the delta to be the smallest gap between any pair of the eigenvalues here. So basically, for this part, for this part is actually if the time capital T here goes to infinity here, then basically this probability is actually also going to be going to infinity is actually going to be this fixed values here, and actually it is having a limiting distribution here. So this is actually the observation that actually people do here. And basically, similar to the classical counterpart, we can also do a more like quantitative version here. So that is basically as long as you have the spectral gap delta here. And basically, I mean, the difference between the probability distribution at time t here compared to the limiting distribution is going to be bounded by 2 over this time t times the spectral gap delta here. So this is actually the trick that, okay, in general, I mean, the behavior of quantum walk is like a unitary dynamics. It does not converge, but actually we have this kind of long enough time capital T here. And if the evolution time is uniformly taken from this interval, it actually having this kind of limiting distribution. And this is also the thing that we are going to apply to the Schrodinger's equation here we use. Okay, so this is just like a quick recap about like the existing, I mean, things in quantum walk. And I think let me also probably here explain a little bit more about the quantum tunneling walk here. Okay, so for the quantum tunneling walk here, I think we do have this kind of assumption that actually all the local minima are global. And basically it is formulated in this kind of sense that we consider the arc mean here. So the arc mean here, the arc mean of the function f here can be written as basically the the union of all these kind of local minima here. And basically as a local minima is basically a point that actually the gradient is 0, and basically the second order, the hashing is actually a a semi-definite matrix here. And basically for such kind of UG here is actually we call this point set as like all the wells here that we study here. Excuse me. So basically after having this kind of definition, okay, so we have this kind of, I mean, all the local minima here, then we can further define, I mean, the distance that we study here. So the distance we study here is basically like the Agamemnon distance. And basically in the sense, actually, we consider a case where all the local minima global here. So basically we have the mean of f here, and we have all this kind of local minima, this kind of x1, x2 until xn here. So basically, we can compare their pairwise distance that is actually characterized by the integral here. So basically, we have, for instance, like x1 and x2 here. Then we can, for instance, define this kind of integral. I mean, this integral is defined by actually the C1 path actually connecting this two local minima here. So basically, for all the pairs of the local minima here, we can define this kind of integral here. And the most important distance that we call the Agamemnon distance here is actually the infimum. I mean, basically, I mean, here, I mean, with the lambda here is taking this kind of all the continuous passes, and basically, I mean, we can take, all among the infimum of all such kind of passes, and we consider such kind of integrals. I mean, for all the pairs of the local minima here, and basically after that, I mean, the minimal Agamemnon distance, I mean, that is actually the S0. You see the S0 in the statement of the main theorem here. So the most important, I mean, the value that actually taking control here is basically this minimum Agamemnon distance is actually the minimum of all this kind of distance between all the UJ and UK for different pairs of the local minima here. So this S0 is actually exactly the value that is actually going to be happening in the exponential term of the convergence rate of the algorithm here. And basically after having this kind of function value, this value on S0 here, we can further look at the local landscape near a well here. So in particular near a well here, I mean for near like a local minimum, basically we can have like a small enough value eta here that actually inside this value here is basically we have each of this kind of local well here, and basically for each of the local well here, we can hence define its local ground state, and we call this for the f well, for the jth well here, we define its local ground state to be the e of j here, and with its eigenvalue to be its eigenstate to be the minimum eigenvalue here. So there are a few facts that, I mean, this is probably more about really about mathematical physics and also a little bit of functional analysis that basically characterize, I mean, the math tools that here basically we use here. So the fact one here that basically for a small enough h here, so as long as you consider such kind of Schrodinger's equation, basically the learning rate, the h here is smaller enough, then basically the point that actually, I mean, we have like for instance, this is like a local well here, and basically we consider this local well, and basically we consider, I mean, we consider this local well, and it actually have like a local eigenstate here. I mean, the ground eigenstate here is going to be looking like this. The point of the fact one here is that, okay, so if you consider, I mean, the local, I mean, the ground state here, I mean, is overlap with all the other local minima is actually going to be exponentially small. So just imagine, okay, so you have this local, I mean, this local well and its corresponding, I mean, local ground state here. I mean, you just consider the tail in terms of the other wells. This part is actually going to be super small. I mean, in general, exponentially small. And if you consider this local ground state here, and basically its overlap with the other local well is also going to be exponentially small here. So the main point actually after making this kind of analysis that in general, I mean, in the analysis is that basically we want to consider the span, basically the span of this kind of subspace spanned by all the local eigenstates. I mean, the local eigenstates of all the ground well, all the local wells respectively. So basically we consider the span of such kind of subspace. The evolution inside this subspace is basically invariant, and basically, I mean, it's basically among this. And if you consider the corresponding, basically you consider Schrodinger's equation, and you consider restriction in this kind of subspace, is that basically, I mean, the probability that you jump to the other like excited states in general is actually quite small. And in general, I mean, inside of this kind of Hamiltonian, if you restrict it to the span of this kind of subspace, I mean, in general, I mean, this basically, I mean, we consider, I mean, the coefficients of this. I mean, basically, is we just call this matrix to be the interaction matrix, and basically, such kind of Hamiltonian really determines the strength of the corresponding quantum tunneling effect. So in particular, I mean, basically, this is like the thing that actually you see like mathematically why actually we do have the assumption that actually all the local minima are actually global here. I mean, this is basically the point. Actually, we do have this kind of definition of the Ackermann distance, and actually after having the Ackermann distance, it is also super important that actually we can actually treat this as a subspace that actually the evolution inside all the local ground states here. So basically, I mean, after having this, basically we can just imagine that actually we can just, I mean, in general, with a very high probability, we evolve inside this kind of invariant subspace here. And actually, in our analysis, we have a little bit further assumption that actually, I mean, we have assumption that actually the eigenvalue difference between any two local ground states is at most O of h to the infinity. So this definition of h to the infinity is basically this value is actually dominated by h to the n for any n larger than 0. So you can imagine this is actually dominated by any polynomial term. So exponentially small in terms of h satisfies this, but in general, I mean, as long as it's actually dominated by any polynomial term, the eigenvalue difference into local ground state, I mean, this satisfies our assumption here. Okay, and also, I mean, there are we also have the assumption that actually there are finite number of paths of the Ackermann length. I mean, connecting all the connecting like each pair of the local minima here. So basically, I mean, I'm not sure if this is a little bit dry here, and actually we do have like assumptions and basically like description here. But I have to say that really, based on this kind of thing, I mean, it's just like, I mean, the theories behind, I mean, in terms of the applied math here, we use functional analysis and also mathematical physics. I mean, in general, I mean, this especially this kind of semi-classical analysis, I mean, this is really a little bit heavy here, and we do have, I mean, we just took a look into like previous literature in terms of, I mean, functional analysis, especially in terms of the Schrodinger's operators. So basically, we just use this kind of tool, and basically what we get for our main result is that, okay, so basically for the Schrodinger's operator, actually it has, for the Schrodinger, basically we consider this kind of behavior, and especially we consider this kind of matrix, H restricted to the subspace spanned by the local ground states here. So basically we can prove an energy gap result, that actually the pairwise difference between all the eigenvalues of this kind of Hamiltonian is actually bounded by this. You see like this actually the main value here, that actually the h here is basically the main dependence is basically this e to the minus s0 divided by h, where this s0 is actually, the s0 is basically this s0, it's basically this s0 that actually we consider Ackermann distance, and this is the minimum among all the Ackermann distance between different local wells here. So basically this is the main result that actually we prove here, and this is really a little bit mathematical heavy, and we have a few assumptions, but I think I have basically briefly explained the ideas behind those kind of assumptions here. And I think basically, I mean, I also introduced the definition, I mean, basically the observation of applying the mixing of quantum walks. And basically this kind of theorem can be naturally applied. You see, okay, so this is good, and this is basically like a special gap kind of result. And this can be naturally extended to analyzing the mixing time of the quantum tunneling walk. And basically, I mean, this is just like the math that maybe you just look familiar compared to the slides for the, just like the mixing property of the standard quantum walk. So basically we, in our analysis, we just extend all of this to this behavior of the quantum tunneling walk, that we have this kind of continuous function, and we have this kind of local wells. And basically a main result that we prove is that, okay, as you can imagine, it's basically dependence, just like, I mean, in terms of, I mean, the overall mixing time complexity is just like O of capital N. The N here is the number of local wells divided by the delta E here. So delta E is the spectral gap here. And actually we do have this kind of dependence in terms of, the difference between the difference of eigenvalues between different local values, we have assumption that this is actually bounded by O of h to the infinity here, and actually we are going to pay a term of n times this kind of thing. So if, for instance, I mean, if your function is like, I mean, one of the local values is super thin and the other is super fat. I mean, I'm making like the eigenvalue difference, I mean, more than this kind of h to the infinity, that can be problematic in general. But I think nevertheless, I mean, this is basically going to be characterized by this part. Maybe, I mean, if it's super large, I mean, in general, this can be something super large. I mean, that is probably not so good. But in general, we can give like a good analysis of the mixing time based on our theory here. And furthermore, okay, so if you know that, okay, your work in general can mix, okay, so it goes to like a mixing distribution that, okay, for all of these kind of points, okay, the limiting distribution in general, I mean, the values are actually not that small here. And actually, as long as you can have like a good property of mixing to like a good distribution here, you can analyze the heating time, right? So basically, you can consider like the heating time is just like, okay, so I know that, for instance, I mean, if you take like appropriate, I mean, overall evolution time capital T here, then basically you know, okay, the limiting distribution is having like a non-trivial probability here. And basically the thing that you can do, and basically you define the heating time to be just like the infimum of all the tau larger than 0. I mean, basically the overall evolution time divided by the corresponding, I mean, probability mass that actually you can reach the corresponding point here. So basically, I mean, as long as we have like a mixing time result, we can also turn this into a heating time result. And after making some calculation here, is that basically, I mean, going to be having this kind of result here. So I guess I have maybe a little bit, I mean, like 5 to 10 minutes. Hopefully, let me actually also very briefly explain what is like the applications, also like the numerical experiments of our work here. So about applications, I guess in general, I mean, we want to talk about, okay, so quantum algorithm, and also we want to talk about non-convex optimization. I guess I think from my perspective, there are two main questions that we want to study. So on the one hand, actually, I mean, I talk about the theories here. You do see that actually the math here to use actually a little bit heavy here. Maybe you want to understand there, for instance, especially there are natural high-dimensional non-convex problems that actually can be solved in our theory. And actually, our theory can give like a good handle for such kind of high-dimensional non-convex problem. On the other hand, we do want to understand. So here, I think for this project, we are talking about like, I mean, basically the aspects of quantum learning. And in general, I mean, we do want to use quantum computing to solve like machine learning problem, optimization problem. I guess is definitely of general interest whether we can solve problem of significant quantum speed up. So the short answer to these two questions is affirmative in briefly, but actually I have to say, I mean, although I do have like affirmative answer to these two questions, I think they are not very satisfactory, as I'm going to explain in a minute. So one application that actually really suits our theory well is that actually we observe that in general for tensor decomposition. So like the tensors, I mean, here the tensor we talk about is like a high order version of the single value decomposition. I mean, so in particular, for instance, let's say we consider like a fourth order tensor. So a fourth order tensor, I mean, like especially like a specific problem in here, like a orthogonal tensor decomposition is that we have the assumption that you have like a tensor, like a fourth order tensor, it can be written in this kind of form, where each of the AG here, they're actually perpendicular with each other, and basically each of them is tensored 4 times, and actually you consider all of this. So basically, I mean, the assumption is that actually I have this tensor given to you, and you can compute this kind of function values, and the required output is, I mean, in general for tensor decomposition, just like in the case of singular value decomposition, I really require you to output all these kind of vectors here. I require you to output all of this A1 to AD here. So in particular, this function is really suits our theory well, because basically for this function, its local minima is global here. I mean, all the local minima is actually having function value 0. So basically, this is actually quite good, and also this is like orthogonal tensor decomposition. We really need to output all of the small tensors, all of the AJs here. So basically, we proved that actually the tensor fourth order tensor decomposition problem basically can be solved in exponential time on quantum computers. So maybe you want to blame me. Okay, so why actually I do want to actually, I mean, we have an exponential time result for solving a problem. I mean, is this actually of general interest? I mean, in general, for the fourth order tensor decomposition problem, it is actually an NP-hard problem. And actually, classical algorithm solving this also takes exponential time. I guess here, this is probably, I have to say that basically for this tensor decomposition result, it is more like it actually our theorem can be useful, can be solved, I mean, this kind of tensor decomposition problem here. But actually, for this tensor decomposition problem, I don't think we have a quantum speed up here. I mean, in general, it takes exponential time. I mean, for fourth order tensor decomposition, maybe other higher order tensor decomposition problem, I mean, there are actually a lot of classical clever algorithm. I mean, not necessarily treat this problem in this kind of optimization way and actually can do better than our classical algorithm. But nevertheless, I think it's basically, you can see that actually our theorem, we have some assumptions, and basically we need to analyze, okay, what is the behavior? What is like the spectral gap here, etc. But basically, I want to make sure that, okay, there are some examples that as basically our assumptions not really something, basically flying in the air, but does not actually exist or whatever. So basically, as long as we have our theory, basically we have a problem whose local minima are actually global, we can solve such kind of problem, basically. So this is the first point, and the other point is actually, we can also talk about the quantum speedup. And actually, we show that actually significant quantum walk, quantum speedup by quantum tunneling walk can actually be, can be possible. That basically, the problem that we studied is basically something like this. So we consider a specific landscape that actually it has two local minima. So one of the local minima is actually just sitting at the original point, but we don't know the position of the other local minima, and basically we want to find the position of the other one. So basically we prove that, okay, assume that you actually have like you have the initial distribution to be the local eigenstate, of the at the original point. Actually, you just evolve this, and basically you want to evolve this and you want to find the position of the other local minima here. So the other local minima can be at any place, and in general, basically we prove that for a specifically designed landscape, this is really like a little bit artificial landscape. But basically the thing is that, okay, the absolute height is actually a little bit significant, but basically we choose the other parameters that actually, the tunneling strength here is actually can be make sure that actually if you evolve the corresponding quantum Schrodinger's equation, it only takes polynomial time to reach from the this local minima at zero to reach the other local minima, that is the place is not known to you, but with a non-trivial probability here. So this is actually somehow a little bit artificial. And I think another caveat I do want to mention is that, okay, so here actually we are having the assumption that actually we need to know the local ground state of the initial, of this kind of well here, basically the well in the whose local minima is actually just the original point. Then basically, we do have this kind of query complexity separation that we prove that, okay, so in terms of the function queries, classically takes exponential queries, and quantumly it suffices to take polynomial queries, and this constitutes an exponential separation in terms of the query complexity here. But there is a caveat I think I do want to emphasize. Actually, you may notice that actually basically the hardness comes to, okay, so there's like a high dimensional space and you don't know the position of the other local minima here. So there's somehow like an unstructured search problem, right? So basically, you want to understand, okay, so this may actually have some kind of behavior of Grover's algorithm, this kind of unstructured search, and you don't know position of like a specifically marked item. So the thing is that actually we make some calculation that basically, we notice that for this specific problem, the initial state, so the initial state here, we assume that actually we have the quantum initial state near a local minimum here. This actually, for this kind of shape, shaped landscape, actually the initial state reveals the directional information that actually it is not, actually preparing this kind of initial state, preparing this kind of initial state can in general be difficult. And if you have this kind of thing, basically for this high dimensional space, if you have this kind of initial distribution, after making a few measurements, somehow you can reveal this kind of direction V here, and this kind of direction can just help you to actually to find the position of this kind of W plus here. So basically this is the other local minimum here. So basically this initial state is actually quite tricky, and actually assuming the existence of this kind of initial state might be super non-trivial.
So
even assuming this can...
Maybe
yes.
I can just say that, so there's like 7 minutes left in the session, so if you would like to have some time for questions, maybe you could wrap
Yes,
up.
yes. Sure. Yeah, definitely. Yeah, so basically, I think I basically finished. I think this is like basically for our work, I basically we conducted some numerical experiments to characterize that actually, okay, the behavior among all the local minima here are essentially exactly having this kind of quantum walk behavior. So, if you have like classical dynamics, it's actually going to up and down. But okay, basically, this is like a figure in the middle. Okay, in the middle is probably going to be looking like this. But in general, the running time actually move from the left-hand side to the right-hand side is actually quite small. And also we conduct numerical experiments on the example that I mentioned in the previous slide. And also we also conduct more quantitative version of our study that basically, as long as the landscape is sharper and sharper, basically the running time of the quantum tunneling walk is actually better and better compared to the classical counterpart. So yeah, I think basically let me make a conclusion here, and basically let me also raise the question from the audiences. So basically, I think we treat our work as like a first attempt and framework for quantum algorithm for non-convex optimization. So I think the algorithm is really simple. We didn't play with the dynamics. The dynamics is just as simple as the standard Schrödinger's equation. And basically, the two main things that actually, if you want to take a notice about the quantum tunneling walk is actually between two of the local minima here. Like two of them, the pairwise thing is basically like the strength is basically dependent on the quantum tunneling, but the overall dynamics among all the local minima is basically having this kind of quantum walk behavior. And I think there are definitely a lot of open questions. I guess, I mean, we do have this kind of we have different assumptions, and basically the math result I think is not totally satisfactory to us. So for instance, I think we do want to, for instance, have like a looser assumptions or maybe more general landscape that hopefully can be studied by quantum algorithm for non-convex optimization. And maybe we can also study some other dynamics. So one of the audiences mentioned that maybe we can consider some dissipation and maybe, for instance, the evolution of some open quantum system. That also makes a lot of sense. I think I have some ongoing work along this kind of line. And maybe hopefully we can also understand quantum speedup on more examples, hopefully which can give more interesting and more real quantum classical equations here. So thank you for your attention. If you have any questions, feel free to email me. So thank you.